move this computer. All right, so hello all. Welcome to this presentation about sustainability in data centers. So some of the reasons that we want to study sustainability in data centers is that the data center industry accounts for around 4% of the global electricity consumption, according to recent reports, and 1% of the global greenhouse gas emissions. And also there is a continuous need to develop more data storage and management, as well as computation capacity. According to Cisco report, it is estimated that by 2023, the number of connected devices will reach 29.3 billion, and half of the network communication will account for machine-to-machine. Last but not least, the rise of edge computing calls for the development of small-sized data centers at scale. So before moving forward, some basics about power and energy. So the two terms should not be used interchangeably. And energy is a function of power over time. And it represents the amount of the work that is being done, while power represents how fast the work is being performed. Typically, there are two energy sources: brown energy that is produced using fossil fuels, and green energy that is produced using renewable energy power sources. In the diagram here, you can see an example of a data center where it makes use of both brown energy through the grid and green energy, while at the same time charging an energy storage device when there is surplus renewable energy, or when brown energy is being obtained at low cost. Some challenges for incorporating green energy in data centers is that it highly depends on natural resources that are controllable by the human factor, and even sometimes they are hard to be predicted. The quality of generated energy can cause intermittent failures in the IT equipment in the event of a power outage. The high cost of deploying power plants is another barrier, and the high cost of energy storage devices makes it hard to support the whole data center operations, since they are an expensive solution. So in order to develop more energy efficient data centers, some approaches are detailed here, and one of them is to use water cooling instead of air cooling when and where it is possible. The fact that water cooling is much more energy efficient and at the same time can support the increased densities in the data centers, and also compute intensive applications, makes water cooling an ideal solution. While on the other side, it is a more expensive solution than cooling. And also, there is a danger in the event of leakage for failures of the IT equipment. Another approach is to make use of renewable energy when when it exists on the site, and to constantly upgrading the IT equipment. A characteristic example is that is found in modern chipset is that CPU cores can be put in sleep mode when not in use. Also, to make use of low-end devices like Raspberry Pis and Arduinos, where this is possible depending on the workloads being executed. And to make use of GPUs instead of CPUs where this is possible, although GPUs are more energy intensive, the high parallelism of GPUs makes application workloads to finish earlier in order to save the extra energy that is spent. So in cases of applications that can be found in edge computing, like video analytics, those are better suited for execution over GPUs, since they require a low response time. So power usage efficiency is a metric that is used in order to evaluate the efficiency of a data center, and it basically represents the proportion of power that is spent on the IT equipment relative to non-IT equipment. And the lower the value it is, it means the more power efficient is the data center. On this diagram, you can see the average PUE of all the data centers on the globe over the years. And as you can see, there is a significant improvement since 2007, where that value was around 2.5 to up to about 1.5 nowadays. To this end, the power optimizations that are being put in place especially in big scale and warehouse data centers contributed to the minimization of this value. So within a data center, energy losses and waste can happen when the electrical energy flows from the grid down to the IT equipment. So energy loss is defined as the energy that is allocated to tasks other than the main computation task. And the waste of energy occurs when the system is performing a task that consumes energy, but no useful output is being produced. So on the diagram here, you can see where losses and waste can happen. Typically, energy losses happen when charging the energy storage devices or the UPS, and also the energy that is spent on cooling the IT equipment is considered as energy loss. Energy waste occurs within the IT equipment when during idle periods of time. Also here, points 1, 2, 3 represents the points where energy measurements can be performed at different levels within the data center. When it comes to the energy optimization of IT components, different methodologies can be used according to the IT component. For example, for CPU, one way is to make use of dynamic voltage and frequency scaling mechanisms that dynamically adjusts the frequency of the CPU cores according to the workloads being executed in order to reduce voltage and therefore save energy. Another approach is to put CPU cores in sleep mode when not in use, when they are idle. For memory, suggested approach is to use DDR5 that is expected to be more energy efficient than its predecessors. And also another way is to slice main memory into chunks in order not to use the whole unit. For hard disk, a suggested approach is to make use of flash drives like SSDs, where this is possible. SSDs are found to be more energy efficient, and they are better suited for delay-sensitive applications since there is a frequent access of the data. For the rest of the applications that are less sensitive, hard drives can be used that can be spinned down when not in usage in order to save some energy. And for network components, again here, network components can be put in sleep mode when not in usage, and smart network components nowadays, they can do this. Some examples of renewable energy sources are wind turbines that can generate energy by the air. And this approach depends on the location and the placement of the turbines, and it is highly variable, which means it is hard to predict the production for a period of time. Photovoltaics make use of solar panels in order to generate energy from solar radiation. And it is intermittent the same way as when wind turbines are, but they are less variable, which means it is easier to predict the production. Hydropower is a process of generating energy with the flow of water. This approach is highly location dependent, but it is controllable since water flow can be controlled. And biomass is the process of generating energy from plants. And this is a very complex procedure that involves a lot of stages, and it takes a lot of time. So energy storage devices are used for storing surplus energy production. And that can be, like I already said, renewable energy or energy that is obtained at low cost. It is an expensive solution in general. So depending on the demand of the data center, it may be hard to rely on those devices. And when those devices are constantly being charged and discharged, this can cause a wear to the device itself by time, which makes the maintenance operation really tough. And energy storage devices are essential in the case that a data center does not have any power solutions and it only relies on renewable energy in order to avoid any power failures. So some suggested solutions found in the literature for developing green data centers. One solution named Parasol was presented in this paper, where the authors introduced Parasol as a solar power data center built for exploration of research opportunities, and Green Switch, an energy-aware scheduler that optimizes the usage of energy sources. So Parasol is connected to both the grid and it is equipped with solar panels, and at the same time it makes use of batteries in order to save the surplus renewable energy. It takes advantage of free cooling by monitoring the temperature within the data center and deciding when to use the AC equipment. And Green Switch is composed of multiple subcomponents, including the predictor that can predict the amount of the generated energy within the day and the amount of workloads that need to be executed. This information are being passed down to the solver that makes an optimal execution of workloads by considering the amount of available energy. Evaluation results suggested that Green Switch can achieve reductions in the usage of grid energy, which therefore results in reduced carbon footprint. Another approach is zero carbon cloud, where data centers that belong to zero carbon cloud zone are located typically near renewable energy sources. This is done in order to avoid the cost of distributing the energy using the power grid. And in that way, ZC Cloud data centers make use of an economic power that is called stranded power, and is typically a power that is delivered with low or negative locational marginal price. When there is power generation and ZC Cloud is available, then submitted jobs are executed by ZC Cloud resources. While in the case that there is a shortage of generated energy, then those jobs are redirected to traditional cloud resources. And finishing with some open challenges and some future directions. So the rapid and continuous development of the cloud edge continuum calls for ways to evaluate the power efficiency of edge premises. The shortcomings of renewable energy calls for the development of efficient green schedulers in the context of edge computing that will be able to support IoT applications. The spatial distance of distributed data centers makes it hard to evaluate efficiency of renewable power data centers without the use of any simulations. So we need some sort of simulators that they should be able to do this at scale. And for load renewables is a form of geographical load balancing where if it can be used in order to migrate workloads or VMs at geographic locations where there is renewable power generation. Thank you for your attention. If you'd like to discuss anything with me, please feel free.